This video will clearly explain some basic quantum programs using Qiskit. First, we look at creating a superposition using the Hadamard Gate. The circuit uses one qubit and one classical bit. This program is expected to output 0 and 1, with about 50% probability each. Next, let's explore the Pauli-X gate, or the CNOT gate. The goal here is to flip the qubit state from 0 to 1. By applying the X gate and then measuring, the expected output is always 1. Now we create an entangled Bell state using the Hadamard and controlled X gates. This 2-qubit circuit should produce outputs 0, 0, and 1, 1, each roughly 50% of the time. This program demonstrates the phase flip using the Z gate. While it doesn't change the measurement outcome directly, it affects interference. In this specific circuit, the phase shift is designed to result in a deterministic output of 0. We can run quantum circuits on a simulator and display the results in a histogram. Here, we run the superposition circuit 1024 times, expecting an equal distribution of 0 and 1 counts, as shown in the histogram. A quantum random number generator uses superposition and measurement to generate a truly random bit. By running the superposition circuit just once, the output will be either 0 or 1, randomly. Controlled operations are crucial in quantum computing. Using the controlled NOT gate, we set the control qubit to 1. This flips the target qubit, resulting in an expected output of 1, 1. Finally, this mini version of Grover's algorithm illustrates amplitude amplification. By marking the state 1 using the Z gate and applying a diffusion step, the probability of measuring 1 is amplified.